Hey guys, and welcome back to this class, Deep Learning Part 5, Recurrent Neural Networks in Python. In this lecture, we are going to talk about the simple recurrent unit, also known as the Elman unit. Before we go into the recurrent unit itself, let's talk about sequences. Why do we want to do that? Because these will look slightly different from the data that we're used to. Recall that our input data X is usually represented with an n by d matrix. That's n samples and d features, so there are no sequences here. Well, let's suppose we did have a sequence. How many dimensions would that require? Call the length of a sequence t. If the observation is a d-dimensional vector, and we have t of them, then one sequence of observations will be a t by d matrix. If we have n training samples, that will be an n by t by d matrix, so that's a three-dimensional object. Sometimes our sequences are not of equal length. This can happen when we're talking about sentences which are obviously of arbitrary length, or perhaps sound and music, or someone's credit history. How can we handle this? We first encountered this problem in my hidden Markov models class. The solution was to store each observation in a Python list. So instead of a 3D matrix, we'll have a length n list, where each element is a 2D observation sequence as a NumPy array. Since Python lists can contain any object as an element, this is okay. So let's get back to our simple recurrent unit. The way it works is this. Take a simple feed-forward neural network with one hidden layer. The input layer and the output layer stay exactly the same. They are actually not part of the recurrent unit itself, but I've included them here to show you what's behind and what's in front. What we want to do is create a feedback connection from the hidden layer to itself. Here's the picture again, but showing the weights. Notice that the feedback loop implies there's a delay of one time unit. So one of the input units into h of t is h of t minus 1. One question you might have is, how big is WH? Just like the other layers, we connect everything to everything. So if there are m hidden units, the first hidden unit connects back to all m hidden units, the second hidden unit connects back to all m hidden units, and so on. So in total, there will be m squared hidden to hidden weights. Here is how we would represent the output of a recurrent net in code or in math. Note that the feedback connection represents a time delay of 1, so the hidden layer takes in both x and its own last value. Notice that the function f can be any one of the usual hidden layer nonlinearities. That's usually sigmoid, tanh, or rel-u. It's a hyperparameter just like with other types of neural networks. The rel-u function can help with the vanishing gradient problem, which we'll talk about in a later lecture. One thing to note is that this is not the Markov assumption. Why is that? Because even though h of t is defined in terms of its previous value can be defined in terms of the value before that, and so on. This also means that h of t needs to have an initial state, h of 0. Sometimes researchers just set this to 0, and other times they treat it as a parameter that we can use backpropagation on. Since the ANO automatically differentiates things for us, we'll treat it as an updatable parameter. One question I get sometimes is, can I add more than one recurrent unit to my neural network? And the answer is, yes, you can. The number of recurrent layers is a hyperparameter, just like how the number of hidden layers is a hyperparameter for a regular feed-forward neural network. The question of how many depends on what's best for your specific problem. We can do this type of layering for all types of the recurrent units we'll see. So that's the Elman, GRU, and LSTM. And that's all there is to it. Just by adding that one recurrent connection, we've created a recurrent neural network. We'll see in the coding lectures how this can already do some amazing things, like exponentially decrease the number of hidden units we would have needed in a feed-forward neural network.